Picture this moment, August 3rd, 1942, right in the heart of Washington, D.C., at the United States Treasury building, where Lieutenant Colonel Kenneth Nichols is about to walk into Undersecretary Daniel Bell's office and make what might be the most audacious request in American history. He needs metal, not just any metal and not just a little bit of it, but an absolutely staggering amount for a project so classified that he can't even explain what it's really for. And when Bell asks the obvious question that anyone would ask, how much do you actually need? Nichols drops a number that makes the room go silent. 6,000 tons of silver. You can imagine Bell's face changing in that instant, trying to process what he just heard. And then he asks something that seems almost comical in retrospect. How many troy ounces is that? Because you see, the Treasury doesn't think in tons when it comes to precious metals. They think in troy ounces. It's their language, their measurement, their entire world. But Nichols doesn't know the answer, and honestly neither does Bell. So there's this awkward pause where two of America's most important officials are sitting there unable to do a simple conversion, and Nichols, growing frustrated because time is running out and there's a war to win, finally says what he's thinking. I don't know how many troy ounces we need, but I know I need 6,000 tons, and that is a definite quantity. So what difference does it make how we express it? Bell leans forward now, his bureaucratic pride wounded, and delivers a line that would echo through history. Young man, you may think of silver in tons, but the Treasury will always think of silver in troy ounces. What makes this moment absolutely extraordinary is what Nichols couldn't tell Bell, the real reason behind this insane request, because hidden behind all this talk of measurements and quantities was a secret so massive it would change the world forever. They needed this silver to build a machine that could separate uranium atoms, a machine that would help create humanity's first atomic bomb. And before their conversation ended that day, the number wouldn't stay at 6,000 tons. Oh no, it would. Balloon to an almost unbelievable 14,700 tons of silver, worth over $300 million in 1942 money, which translates to nearly $6 billion in today's currency, all borrowed from the American people's reserves to construct magnets the size of entire houses. This is the story of the Calutron, one of the most desperate, brilliant, and massive solutions ever devised to solve what seemed like an impossible problem during the Manhattan Project. And to understand why they needed so much silver, we need to go back and understand the challenge these scientists were facing in 1942. Everyone working on the bomb project knew that uranium-235 was the key, the secret ingredient that made atomic weapons possible, because when a neutron slams into a uranium-235 nucleus, something incredible happens. The nucleus splits apart violently, releasing enormous amounts of energy along with more neutrons that go on to split even more atoms, creating what scientists call a chain reaction. And this chain reaction was the fundamental principle that would power the atomic bomb. But here's where the problem gets really brutal. Natural uranium, the stuff you dig out of the ground, contains only 0.72% uranium-235, less than 1%, while the remaining 99.28% is uranium-238, which unfortunately won't sustain the chain reaction needed for a bomb. So to actually build a weapon that works, you need uranium that's been enriched to at least 90% pure uranium-235, which means you have to separate two isotopes that are essentially identical twins. Think about how insane this challenge really is. Uranium-235 and uranium-238 have the same number of protons, the exact same number of electrons, identical chemical properties. They behave the same way in every chemical reaction you can imagine. And the only difference between them, the only thing separating a useless element from the most powerful explosive material ever conceived, is 3 tiny neutrons tucked away in the nucleus. Uranium-238 has 146 neutrons, while uranium-235 has just 143. And that microscopic difference in atomic mass, that 3-neutron gap, is all you have to work with. So the question becomes, How on earth do you exploit that tiny difference on an industrial scale large enough to build actual bombs? Multiple approaches were being explored simultaneously because nobody knew which one would work. Gaseous diffusion, where you force uranium gas through thousands of filters; thermal diffusion, where you use temperature differences to separate isotopes; centrifuges that spin at incredible speeds. But every single method faced enormous technical hurdles. Each one had serious problems, and none of them were guaranteed to work in time to actually affect the outcome of World War II, which meant the Manhattan Project was essentially gambling billions of dollars and countless man-hours on technologies that might not pan out. Then Ernest Lawrence entered the picture. And this is where things get interesting, because Lawrence was already famous as a physicist at the University of California, Berkeley, and as the inventor of the cyclotron, which was a circular particle accelerator that could smash atoms together at high speeds. And in 1941, a British physicist named Mark Oliphant visited Lawrence and told him about Britain's atomic research, explaining that the British MAUD committee had determined an atomic bomb was theoretically possible, but they desperately needed enriched uranium, and they needed it fast, or the war might be lost. Lawrence had an idea that probably sounded completely absurd to most people: electromagnetic separation, using the power of magnetism to physically separate uranium isotopes based on their tiny mass difference. And while the principle was elegantly simple in theory, actually doing it was another matter entirely. Here's how it would work. First, you ionize uranium, meaning you give it an electric charge by stripping away electrons. Then you fire these charged uranium ions through an incredibly powerful magnetic field. And because charged particles curve when they pass through magnetic fields, and because the amount of curving depends on the particle's mass, the heavier uranium-238 ions will curve less, while the lighter uranium-235 ions will curve more. So you position collection cups at different points along the curve, and theoretically you can catch them separately. It was essentially taking a mass spectrometer, an instrument about the size of a desk that scientists used in laboratories, and scaling it up to industrial proportions capable of processing tons of uranium, which had never been attempted before. Lawrence converted his old 37-inch cyclotron into the first prototype, and they gave it a name that honored its California origins: the Calutron, short for California University Cyclotron. And on December 2, 1941, just 5 days before Pearl Harbor would drag America into the war, they switched on the Calutron for the very first time and held their breath. It worked. The uranium beam reached the collector with an intensity of 5 microamperes, which might not sound like much, but it was proof of concept, confirmation that Lawrence's wild hunch had merit, and that electromagnetic separation could actually function. And by January 1942, they had produced 18 micrograms of uranium enriched to 25% purity, which was 10 times more concentrated than any previous enrichment method had achieved. But now comes the truly staggering part. There's an enormous difference between proving a scientific principle works in a small laboratory setting and actually enriching enough uranium-235 to build functional atomic bombs, because the Manhattan Project didn't need micrograms of enriched uranium. They needed kilograms of weapons-grade material, and to get there they would need to build massive Calutrons. Not just one or two, but hundreds of them operating simultaneously around the clock. And that created an immediate crisis, because these machines required enormous electromagnets with coils wound from highly conductive metal. By mid-1942, the Manhattan Project's chief engineer, Colonel James Marshall, and his deputy, Kenneth Nichols, were staring at a brutal reality that threatened to derail the entire project. To build the electromagnetic separation plant, which had been codenamed Y-12 and would be constructed at Oak Ridge, Tennessee, they needed approximately 5,000 short tons of copper for the magnet windings, because copper was the best electrical conductor readily available, and it was absolutely essential for creating the powerful magnetic fields required. But copper was in desperately short supply across the entire country. And when I say desperately short, I mean, every single industry and military branch was fighting over whatever copper existed because World War II had created an insatiable demand for this metal. Electrical wiring for warships and naval vessels, airplane manufacturing, tank production, communications equipment that kept military units connected, ammunition casings for bullets and shells. Copper was literally everywhere in the war effort, and everyone wanted it. The metal was rationed, strictly controlled by the government, fought over by competing interests, and the Manhattan Project, despite its top-secret status and ultimate importance, simply couldn't get 5,000 tons of copper because it was genuinely impossible. The copper didn't exist in available form. So Nichols and Marshall had to start looking for alternatives, and that's when someone asked the crucial question: what else conducts electricity almost as well as copper? The answer was silver, and here's a fact that surprises most people. Silver is actually the most electrically conductive element on planet Earth, even better than copper, though the difference is relatively small with an 11-to-10 ratio, meaning 11 parts of silver could replace 10 parts of copper in terms of conductivity. So to replace their needed 5,000 tons of copper, they calculated they would need approximately 5,500 tons of silver, but this raised an obvious problem. Where in the world do you find 5,500 tons of silver in the middle of a global war when resources are stretched to breaking point everywhere? The answer lay in the United States Treasury, which held massive reserves of silver bullion at the West Point Bullion Depository in New York. Tons upon tons of gleaming silver bars, with each bar weighing 1,000 troy ounces, or about 31 kilograms. And this wasn't just any silver sitting in a vault somewhere. This was silver that backed the nation's currency, that represented the accumulated wealth of the American people, that was guarded more carefully than even gold reserves because it was fundamental to the country's financial system. Nichols received authorization to approach the Treasury and request what would become one of the most unusual loans in history. And that's how we arrive back at that fateful meeting on August 3rd, 1942, when Nichols walked into Daniel Bell's office and tried to explain, without revealing any classified details about atomic bombs or uranium enrichment, that the War Department needed to borrow silver for a project of the absolute highest national importance. After that memorable exchange about tons versus troy ounces, Bell agreed to provide the loan, but he wasn't about to hand over the nation's silver reserves without strict accountability measures in place. The silver would be weighed down to the individual troy ounce. Monthly reports would be mandatory. Armed guards would accompany every single shipment from depository to factory. And at the war's conclusion, every ounce would have to be returned to the Treasury. The final amount borrowed wasn't the original 6,000 tons that Nichols first requested, because as the Manhattan Project's plans grew more ambitious and more Calutrons were added to the design, the need for silver expanded exponentially until it reached a truly astronomical figure: 14,700 short tons, which equals 13,300 metric tons, or when expressed in the Treasury's preferred measurement, 430 million troy ounces of silver, and at 1,942 prices, this represented a value exceeding $300 million, equivalent to nearly $6 billion in modern currency, making it one of the largest financial transactions in American history. And think about the audacity of this. The United States government was essentially loaning itself a fortune in silver to build a weapon that might not even work, based on theories that hadn't been fully proven, gambling everything on the hope that science and engineering could solve problems nobody had ever faced before. The silver arrived from the depositories in those 1,000 troy-ounce bars, each one gleaming and surprisingly heavy at 31 kilograms, and they were transported under heavily armed guard by railway to the Defense Plant Corporation facility in Carteret, New Jersey, where workers melted down these priceless bars and cast them into cylindrical billets, which were then shipped to Phelps Dodge in Bayway, New Jersey, where they underwent a process called extrusion, being forced through dies under enormous pressure until they emerged as strips, each strip measuring 0.625 inches thick, 3 inches wide, and 40 feet long. Eventually, 258 railroad car loads of these silver strips traveled under armed guard to Allis-Chalmers in Milwaukee, Wisconsin, where teams of engineers carefully wound the silver strips onto enormous magnetic coils and sealed them into welded casings to protect them from damage and corrosion, with each completed coil being massive in scale, weighing several tons and designed to generate the intense magnetic fields necessary for separating uranium isotopes. And finally, these completed magnets made the journey to Oak Ridge, Tennessee. But here's something interesting. They traveled on unguarded flat cars this time, completely exposed, because once the magnets were sealed in those anonymous painted casings, nobody could tell what they were made of. They just looked like industrial equipment, nothing special, nothing worth stealing. At Oak Ridge, construction of the Y-12 electromagnetic separation plant was already well underway, and the scale of this facility was absolutely staggering. It covered 825 acres in Bear Creek Valley, an isolated location chosen specifically because the surrounding ridges might help contain a major explosion or nuclear accident if something went catastrophically wrong. And the plant would eventually comprise 9 major process buildings plus 200 support structures covering nearly 80 acres of floor space, making it one of the largest industrial facilities ever constructed. The Calutrons themselves were arranged in configurations they called racetracks, so named because when you looked at them from above, the magnets formed oval tracks similar to horse racing tracks, and each racetrack contained multiple Calutron tanks arranged in a circular formation, and inside each tank, uranium tetrachloride was heated until it vaporized and then ionized by adding electrical charge. The ions were accelerated through a vacuum chamber and then deflected through 180 degrees by those massive silver wound magnets, with the heavier uranium 238 ions curving less and the lighter uranium 235 ions curving more until they struck different collection cups positioned at precise points. And then the separated uranium was chemically recovered from the collectors and processed further to increase purity even more. But turning this theoretical concept into actual working reality required solving literally countless engineering problems that nobody had anticipated. The vacuum tanks, which weighed 14 tons each, kept creeping out of alignment because the magnetic forces were so powerful they would physically move these massive steel tanks, sometimes shifting them 3 inches or more, forcing engineers to develop better fastening systems to hold them securely in place. Moisture that somehow got inside the magnet coils despite all precautions would cause short circuits and rust formation, which meant magnets had to be completely torn down, meticulously cleaned, dried, and rewound, costing precious time and resources, and mysterious debris that scientists informally called gunk and crud would condense inside the vacuum chambers over time, blocking the narrow slits and causing the carefully focused ion beams to spread out and lose effectiveness. The ion beams themselves generated intense heat, even though their electrical intensity was relatively low, and over many hours of operation this heat could actually melt the collection cups where the enriched uranium was gathering, so engineers had to add elaborate water cooling systems to prevent damage. And detailed procedures had to be developed for cleaning all this equipment regularly without contaminating or losing any of the precious silver in the process. And speaking of the silver, special handling procedures were instituted that sound almost obsessive, but were absolutely necessary. When workers needed to drill holes in silver components for assembly or repairs, they placed sheets of paper underneath to catch every single tiny filing and shaving, and at the end of each work shift, all this paper was carefully collected and the silver was chemically recovered from it. When machinery was dismantled for maintenance or cleaning, every surface that might have touched silver was meticulously wiped down and the rags were saved for silver recovery. And eventually engineers realized that even microscopic amounts of silver had fallen onto the floor over months of operation. So they actually ripped up the floorboards beneath the equipment and burned them to recover trace amounts of silver from the wood. because Kenneth Nichols had to provide monthly accounting reports to the Treasury, documenting every single troy ounce, and the scrutiny from Treasury officials was incredibly intense. The responsibility was enormous, and losing significant amounts of silver was simply not an option. The first Alpha racetrack, which performed the initial stage of enrichment, became fully operational in early 1944 after months of extensive debugging and troubleshooting, and by spring of 1944, multiple Alpha and Beta racetracks were running simultaneously, with the Beta racetracks taking the partially enriched uranium produced by the Alpha units and enriching it even further until it reached that critical 90% purity threshold required for weapons-grade material. One of the most remarkable and often overlooked aspects of the entire Y-12 plan operation was the nature of its workforce, because Tennessee Eastman, a chemical company, was hired to operate the facility, and they recruited thousands of workers from the rural areas surrounding Oak Ridge. And most of these workers had only high school educations at best. Many had never operated complex machinery before, and a significant number were young women, some barely out of their teenage years, who became known affectionately and historically as the Calutron girls. These women sat at control panels in rotating shifts that covered all 24 hours of every day, monitoring dozens of dials and gauges, adjusting knobs and switches with precision, keeping those uranium ion beams focused and stable hour after hour. And the work required intense concentration and strict discipline because the control panels were incredibly complex with dozens of instruments that all had to be monitored simultaneously, and a small fluctuation in any parameter could ruin many hours of enrichment work and waste precious uranium. But here's the truly astonishing part that really drives home how unusual this entire operation was. The Calutron girls didn't know what they were actually doing. They had no idea they were enriching uranium or working on an atomic bomb, because for security reasons that were considered absolutely essential, they were told nothing about uranium, nothing about isotopes, nothing about nuclear physics or weapons. They were simply trained through repetition and practice to keep the instrument. Needles within specific green zones marked on the dials. Dial A had to stay between these two numbers. If dial B started dropping, you immediately adjusted knob C to bring it back up. Follow the written procedures exactly. Don't deviate. Don't ask questions. Don't try to understand the bigger picture. And as Kenneth Nichols later described it with a mix of admiration and unease, they were trained like soldiers not to reason why, but simply to execute orders perfectly. And here's what makes this story even more incredible. They were exceptionally good at their jobs, remarkably so, because initially scientists from UC Berkeley operated the Calutrons themselves in order to work out technical problems and establish the baseline operating procedures, but then they handed control over to these young Tennessee Eastman operators. And Kenneth Nichols started comparing the production data from both groups and noticed something that frankly shocked him. The young women operators were consistently outproducing the PhD physicists by significant margins. Nichols mentioned this surprising finding to Ernest Lawrence, who was understandably skeptical because how could high school graduates with minimal training possibly outperform highly educated scientists who understood the fundamental physics? So they agreed to settle it with a direct production race. Lawrence's trained scientists versus what some people were calling the hillbilly girls, and Lawrence lost decisively. The reason for this outcome was actually quite simple when you think about human psychology and work habits. The scientists couldn't help themselves because when a dial started fluctuating or an instrument reading seemed odd, their scientific training compelled them to stop and investigate why it was happening. They would spend valuable time analyzing data, forming hypotheses, testing theories, trying to understand the root cause, which is exactly what good scientists should do in a research setting, but the young women who had been trained purely on procedural execution would simply notice the fluctuation, make the prescribed adjustment according to their training, and immediately move on to monitoring the next instrument, keeping the entire system running at peak efficiency without interruption. It was a profound lesson in the critical difference between understanding complex systems and executing operational procedures. The scientists deeply understood the physics and theory behind what was happening, but the young women were superior at actually executing the process and maintaining consistent production. And both skills were necessary, but in this particular context, reliable execution turned out to be more valuable than theoretical understanding. Years later, after World War II had ended and atomic bombs had been dropped on Hiroshima and Nagasaki, killing hundreds of thousands of people and forcing Japan's surrender, many of the Calutron girls finally learned for the first time what they had actually been doing during those long shifts at the control panels. They discovered they had been separating uranium-235 from uranium-238. They had been helping to build the atomic bombs that ended the war, and their reactions varied dramatically. So, me felt enormous pride that their work had helped save American lives by ending the war more quickly. Others felt horror and guilt about contributing to weapons that killed so many civilians, and all of them were absolutely astonished to realize that the fate of the war, and perhaps the fate of the entire world, had in some small but real way rested in their hands as they sat at those control panels keeping needles in green zones. By July 1945, after months of continuous operation and countless technical challenges overcome, the Y-12 plant had finally produced enough enriched uranium-235 for one complete atomic bomb, and that uranium became the explosive core of Little Boy, the gun-type atomic bomb that was loaded onto the B-29 bomber Enola Gay and dropped on the Japanese city of Hiroshima on August 6, 1945, and the bomb contained approximately 64 kilograms of uranium enriched to about 80% uranium-235, and when it detonated at 8:15 in the morning local time, it released energy equivalent to roughly 15,000 tons of TNT explosive, instantly destroyed 5 square miles of the city, and killed an estimated 70,000 people in the initial blast and firestorm, with tens of thousands more dying in the following weeks and months from radiation sickness and injuries. 3 days later, on August 9th, a plutonium-based bomb called Fat Man was dropped on the city of Nagasaki with similarly devastating results, and on August 15, 1945, Emperor Hirohito announced Japan's unconditional surrender in a radio broadcast, bringing World War II to its conclusion after 6 years of unprecedented global carnage, and the Y-12 plant had achieved its mission. The Calutrons had worked despite all the doubts and technical challenges. Electromagnetic separation had proven viable for producing weapons-grade uranium, but now came a different kind of reckoning. What to do about all that borrowed silver? After the war ended, the electromagnetic separation process was gradually abandoned in favor of gaseous diffusion, which turned out to be more efficient and economical for large-scale uranium enrichment, so the Calutrons were systematically dismantled, the massive magnets were carefully disassembled, and the silver had to be meticulously recovered and returned to the Treasury because that had been the agreement from the very beginning. Every coil was painstakingly unwound. Every component was disassembled and cleaned with almost obsessive care. The silver strips were recovered and weighed and inventoried. Workers ripped up floorboards beneath the machinery, just as they had done during operations, and burned them to recover even microscopic traces of silver. Cleaning rags were processed chemically. Every conceivable effort was made to account for every single troy ounce because the Treasury Department was watching carefully and they expected their silver back. In the end, out of 430 million troy ounces that had been loaned to the Manhattan Project, only 155,645.39 troy ounces were permanently lost, which represents less than 0.036% of the total, an absolutely remarkable recovery rate that satisfied even the meticulous Treasury accountants. And the missing silver hadn't been stolen or misappropriated. It had simply been lost to the enrichment process itself over years of operation. Some had vaporized from the intense heat, some had chemically bonded with other materials in ways that made recovery impossible. Some was embedded so deeply in equipment and structures that extracting it would have cost more than the silver was worth. The Treasury was satisfied with this accounting. The silver was officially returned, the unprecedented debt was paid. Though interestingly, the very final pieces of silver weren't actually replaced until May 1970, nearly 30 years after that initial loan, when the last 67 tons of silver were finally swapped for copper and returned to the Treasury, closing the books on one of the strangest financial transactions in American history. The story of the Calutron and the silver loan is so much more than just an interesting wartime anecdote or a footnote in atomic history. It's a powerful testament to what human beings can achieve when brilliant engineers and determined workers face seemingly impossible problems with severely limited resources and the pressure of a global war bearing down on them. And the electromagnetic separation principle that Ernest Lawrence developed for the Calutron continues to live on in modern science. Mass spectrometers used today in laboratories around the world employ the same basic concept that Lawrence pioneered back in 1941. Ionize particles, pass them through carefully controlled magnetic fields, and separate them based on their mass. And these sophisticated instruments are now absolutely essential tools in medical research for identifying diseases, in environmental monitoring for detecting pollutants, in forensic analysis for solving crimes, and even in space exploration for analyzing the composition of distant planets and moons. So Lawrence's desperate wartime innovation created technologies that benefit humanity in countless peaceful ways. The Y-12 facility still exists today in Oak Ridge, Tennessee, though it's now called the Y-12 National Security Complex and is operated by the Department of Energy's National Nuclear Security Administration. And while it no longer enriches uranium using electromagnetic separation, it remains critically important because it's responsible for maintaining and producing components for every nuclear weapon in the United States arsenal. So in a sense, the legacy of those Calutrons and all that borrowed. Silver continues to this day in America's nuclear deterrent. But perhaps the deeper story here reveals the extraordinary lengths that governments will go to when seeking technological advantage during wartime, because borrowing 14,700 tons of silver from the nation's financial reserves was simultaneously an act of desperation and an act of faith. Desperation because the alternative was potentially losing the race to develop atomic weapons, and faith that the science would actually work, that the engineering challenges could be overcome, that the massive investment of resources and effort would ultimately pay off in victory. And in this case, that faith was rewarded, though at a terrible cost in human lives. The story of the Calutron girls reminds us of something profound that often gets lost in the grand narratives of history. The great achievements that shape our world frequently rest on the shoulders of ordinary people doing extraordinary work without recognition or even understanding of their contribution, because those young women sitting at control panels hour after hour, shift after shift, keeping instrument needles carefully positioned in green zones, played a role every bit as critical as the famous scientists who understood the physics and theory. And there's a lesson in that about how execution and discipline matter just as much as brilliance and innovation. How the people who actually make things work day after day are just as essential as the visionaries who conceive bold ideas. And how history is truly made by countless individuals whose names we'll never know, but whose dedication and skill made impossible things possible.